Next, we have Jon Thielen, who will be continuing our exploratory data analysis elements, but now looking at multidimensional data. And so we'll be getting our hands wet with a different set of tools here. And all of this is in prep so that then when we get to working with our data later this afternoon, you'll be able to start putting your tool sets to use in these ways, and then being able to do so with a room full of and online tool of folks to help us enlighten this work. Jon.
Excellent. All right, so this is the multidimensional X-array NetCDF complement and continuation to the prior talk that was focused on pandas and tabular data. So going back, in any good storytelling, are we finally good? I am so sorry about those issues. Yay, we can continue. Woohoo! So, as I was saying, any good story that is a sequel needs to have callbacks. So, following up from our prior presentation, this is the same sort of diagram of our general framework for exploratory data analysis. We have these 4 steps of locating and reading the data, examining metadata, examining your individual variables, and examining the relationships between your variables. And if we want to look at how this can be with X-ray, like the bare bones minimum, X-ray can do each of these steps with user intervention, of course, and previewing and interacting with the HTML output in a Jupyter Lab cell. But most of these things can be done with single lines of code if you're just looking for the initial starting point. So this is sort of setting the stage for what we'll be working on interactively in Jupyter Lab. But the key idea is that X-ray has a function for opening your data set, be it from file or URL. Also, this can be taken place if you have a separate data access library, such as Siphon. Those have specific methods that output an X-ray data set. If you want to examine the metadata and explore a particular data set, it's just the variable in a cell and look at the HTML representation. And if you aren't in a capacity where you can have the nice interactive preview, there's usually enough information in the text output via print that's useful as well to not forget. If you want to look not just at the data set as a whole, but as a specific variable, you can go into the attribute of the Python object to get to your variable. You can also do the nice little bracket with a text string. And finally, examine relationships among variables. This one takes a lot of different forms, but as an example, if you want to have a scatter plot between 2 variables just to see a quick interrelation between them, that's what that can look like there. And again, these are intentionally simplified. We'll be doing a bit more detailed in a bit. And again, our general model that's going to guide how we think about and interact with multidimensional data is this NetCDF model and how X-ray implements it. So this figure should look fairly similar to what was before, where we have a file overall, and then within that file there are various groups of our data, and then each group is sort of characterized by these 4 different things. We have attributes describing what is contained within that group or the properties of the data set itself. We have dimensions that outline the structure, the multi-dimensional data portion. The variables, the actual content of the matter, and then coordinates, which help us contextualize and have data. It's a form of metadata describing where and when and perhaps how our data came about. And each of those respectively have attributes. And if we want to visualize it, this is a nice figure that a lot of X-ray documentation likes to showcase. I think it does a really good job of picturing what we mean by regular gridded data, where you have some number of dimensions, in this case 3, for your core data variables, for example, temperature and precipitation. Then you can have coordinates that describe, for instance, a geospatial location, latitude, longitude, along 2 of the dimensions of the data, where perhaps the other dimension, as we can see here, is time. So we have x, y, and t as dimensions. We have coordinates, perhaps belonging to x, y, and t themselves, dimension coordinates, or we have coordinates that don't belong to dimensions, which we can call auxiliary coordinates, but they still help describe our core data variables. And each of those things can sort of be captured in a data array. That's an object we'll be working with a little bit, and a bunch of different variables all together. That's what we call a data set. And a few other quick little caveats. There are plenty of formats other than netcdf, but this model really helps inform how we think about and work with this. So that's what we'll be focusing on here. If you, for example, have a ZAR data set, ZAR store, a lot of those can follow same conventions and be read in very nicely. There are packages for working with grib in this same context, such as cfgrib. I don't think that's in our environment, unfortunately, today, so you may not be able to play with grib files, but hopefully there is enough other resources at your disposal that we can work with this. Also, a key thing is that you may, if you're from a GIS community, you may hear the term raster data. This is very much interrelated. Usually we talk about raster data. Those are 2D images, a special subset of multidimensional data, but a lot of those we can still analyze within this X-ray framework. Or conversely, if you really like your GIS tools, you can slice and dice and do some things with pre-processing to get rasters that you then analyze in another context. And finally, this is all having a nice rectangular structure. There are a lot of use cases where we have grids that follow different structures that aren't rectangles. We have hexagons and various other shapes. And there are emerging community efforts to handle these in X-ray, but because of the complexities involved, we're not going to touch on them here. And so now, that was just a quick little slide introduction. Let's actually get to some Jupyter Lab stuff. So feel free to follow along with the simplified example that's in the notebook that if you have loaded the notebook this morning, you should see it in there under the second session for Monday. I have a bunch of different alternative data sets in there commented out. If you wanted to switch around and uncomment one of those to play with them, I'll describe what those are once we get to the notebook. Or if you have something that you can either that's small enough to upload to the Science Gateway lab, or if you know where you can get to it via a remote service, you can plug in that as well. Anything that you can get into X-ray will be good enough to play with for this little exercise here. So let's switch over and hopefully I do not mess anything up. Okay, so I'm noticing quick here we have some chat. Are we good on that end? Anyone need a quick check-in about anything we've talked about so far before getting into the meat of working on the notebook? Okay, seeing no hands raised, seeing nothing online. I did not want to click that button. I am having such a great time with my user interface here today. So, again, this is same interface that we used before in the prior talk. We're going to start out as before, inputs. Recommend that good old Shift-Enter to get started. And then another little thing that I want to make sure for anyone who's not used to a Jupyter Notebook interface, I guess I call it my favorite, but I kind of need to have Shift-Enter as the most practical. But Shift-Tab. I want to make sure to highlight that as just a general quality of life thing that's really nice in working with a Jupyter Lab interface. Shift-Tab inside of some function or method call usually pulls up a quick doc string about that function. And so, for example, this open data set, this argument that we're passing by default is a file name or object, and we can see because X-ray in this portion has typing, it can take a string, it can take something that looks like a path object, it can take in a buffered IO object, or also an internal class to X-ray called an abstract data store. So this single method can take in a lot of different things, and I recommend you go to the documentation. I won't be able to go into full detail about what all of those things you can do. For now, the main things we'll be working with is passing a file path string or a URL to something that is perhaps hosted by OpenDAP on a thread server or elsewhere. So I'm going to be using this IRMA GFX example that's from MetPy's test content. but feel free to swap this out and you can play around with any, and I'd be glad to answer questions about any of the data sets we encounter along the way. So we'll shift tab both of those, and I need to, it's really loud to me when I'm doing those shift clicks. Is that something I should be avoiding on your end? Okay, you're fine. Okay, that is a me issue. So let's get to the heart of the matter, which is the HTML representation of our X-array data set. This is where a lot of those first parts of exploratory data analysis can all be done just by clicking and playing around in this nice little HTML representation. So along the very top here, we have the dimensions that are contained within this data set. You can see something interesting from the very start that you think, okay, we have various dimensions that correspond to our various space and time dimensions. So we have time, latitude, and longitude. Those make sense. But why do we have two different isobarics? Because if you notice, they're different lengths. So they're describing slightly different dimensions that in space represent the same physical type of dimension, but in a data representation, they're describing different shapes of arrays, or different, perhaps, coordinate alignments of arrays. And shout out for a later talk on CFX array and related tools. There's some stuff that you can help with this. I won't be going into those details here, but stay tuned. There's some fun stuff to help you work with that even easier. Because, for instance, if you loaded the GFS example, you'll get a dimension list that probably fills half my screen. But here, you don't have that. Wanted to pick something that had just enough complexity to show that off. And then moving on from dimensions, we can see that most of the coordinates of this particular data set are aligned with those particular dimensions. So we have a data set that's pretty much all with coordinates that are dimension coordinates. If you pick a different data set, that won't always be a case. You can see that there are often coordinates that exist as combinations of other dimensions or are perhaps redundant, describing the same dimension in a slightly different way. That's often the case when you have projected data, where you have an x and y dimension, but you have auxiliary coordinates of latitude and longitude. And then the next section is our data variables. And most of these right here have fairly long names, so you'd have to hover over them to sort of preview the full name. You can see over here, it'll describe which dimensions they exist along and what their data type or D type is. And then these two little buttons over here, two little icons, are things that are quite useful. This first one, the little paper with the lines on it, that is our attributes show and hide button. And here we can see our metadata, our attributes about this particular variable. If we click this little stack, we will see right now, because this particular data set, we haven't loaded all of these bytes basically of the file into memory yet. We just know where they're at. It just will tell us how many values we have in their D type. Once we actually load it, you'll be able to usually see some form of preview here. And we'll be getting into that, and you'll see in more detail later on. And so let's see here. This is one other thing that wasn't quite mentioned in the sort of netCDF, those 4 different things, but it's something that X-Ray has been working on a lot, is calling out indexes specifically. We won't worry about those in detail here, but there are a number of geospatial applications that having more advanced indexing is very helpful for. If you're curious about that for your particular problem, we can have questions and conversation about that outside this session. And finally, we have global attributes, and these are also very useful to look through. And so I realize I answered the question I set for ourselves here, is that what informations for exploratory data analysis can we clean from just this preview? And it's most of it. But that is also very much a function of what exists in your data set already, what exists in the netCDF or other file type that is there. If I were to pull, for example, a WRF file, there is a lot of metadata there, but it's a bit harder to parse. It's a bit harder to work with. And so there are a lot of cases where by previewing it this way, you can diagnose the quality of your metadata or how useful your metadata is for your problem, and that will help set the stage for further exploratory analysis or knowing what initial steps you need to take in later explanatory analysis. And I won't talk through this just because I realized we're at time, or we're going through time not quite as I was planning. But if you want to read through those details about metadata conventions, that content is right here. So without further ado, let's continue on at a little bit faster pace. An initial data quality check, we can do a couple things first. If we want to just extract a variable, that looks like this. Very similar to the dataset case. It's just structured to prioritize the values when we're looking at a particular variable. If we want to check for just straight up missing values that are represented as nulls or nans, we see something like this, and this is what I was talking about as the actual content hiding under this little silo or stack icon. You can see a representation. That's not very helpful for multidimensional data. So we usually want some kind of summary of this. And one thing we can do is just sum all of these, because in Python you can sum booleans and they get treated as integers. It's 0. There are no missing data values in this particular data set, which is kind of expected. This is a GFS forecast for a particular date and time. Usually your core fields are not going to have missing data, usually. The other thing we can do is we want to sort of categorize the distribution as a quick check of, are we thinking of this in the right units, in the right bounds? Does this make physical sense? And generally speaking, considering that this contains all the levels of the atmosphere that include in the GFS, this does make sense generally as a range of temperature values. So if we want to actually start looking, because when we get to multidimensional data, we really want to see pictures. And so when we have more than 2 dimensions, we can't see a picture right away usually. We want to subset down to particular slices or samples within that whole collection. And so here, first, as an example, if you're used to working with NumPy, you can just specify indices, and that's similar to what we did with iloc in the previous pandas example. And you can see this one, we just stuck out our first time, are left with our other dimensions. And for example, if we want the bottom vertical level, we can do a -1 for the next index. And now we are down to something that's 2D. However, as was noted before, usually, unless you're just trying to grab something quick to preview, it's usually best to do something that's position or label based. And with Xarray, we do that primarily with the .sel or cell selection method. And so if we want to select a time, we can specify our time, dimension, coordinate, name, and our label that we want to select. And we see something very similar to last time. But this time we were able to specify it using an actual time, not just an index within a particular array. And we can include multiple at once as well. So let's grab 500 millibars at this time, and we have a nice 2D temperature selection. And finally, what I was working up to this whole time is we can get a picture. And with Xarray, and there's ways to do this in pandas too, but instead of always passing something into a matplotlib function, if you're doing exploratory analysis, you can do these quick little .plot methods. I would not recommend using the built-in plotting methods here for doing any sort of rigorous publication quality figures. That's usually more a hindrance than a help. But when you're just exploring your data, be able to just do .plot at the end is really convenient. And so we can see at 500 millibars, this is our temperatures. We have a nice cool trough up here and this little warm spot down in the corner. I wonder what that is. And if we want to look at relative humidity, I wonder what's in the corner of our domain. You can tell by the example name what this is. It's Hurricane Irma. And so here we've performed the examine individual variable steps of EDA. I'd encourage you, as you want to explore here, is how can we interpret multiple of these figures together to sort of accomplish that fourth step of EDA? Something to keep in mind. And then another thing you can do, and this is starting to, depending on how you interpret it, tread into out of what is strictly exploratory. But when I explore a data set, I still like to do quick calculations and summaries, so wanted to bring it up here as well. So for example, let's look at a subset of the corner. This is a little trick for doing faceted plots. Is that if you throw in a column argument with a particular group or a particular dimension that has a low count, and you decide how to wrap, you can actually see a bunch of different copies of it all within one call. And so, for example, we subset using a range into the corner of our domain, and then we subset our vertical level and then plot across time. So that's what these two lines of code are doing. And again, if you want to learn more about what these things are doing, you can try to quick do your shift tab. It's not cooperating with me at the moment. I must be too deep into my chain of commands here. But there's lots of good stuff on the X-ray tutorial and X-ray documentation. So another exploratory thing is just a quick question is like, what is the minimum 500 millibar or hectopascal geopotential height at each time in this little subset? And we can do something like that with this .min method. And so what's going on here is if we can minimize over those two dimensions, and then we get another 1D data array that we can just plot. And it interprets it automatically and makes us a line plot. And this is a very quick, rough figure, but something that may be useful as you're exploring a data set. And so let's break apart what's going here. So again, this portion of that line of code, the geopotential height portion with the brackets, selects the data variable. The dot cell allows us to subset or select what particular level or layer along that coordinate axis we're choosing. And then this min, this reduction or aggregation or summary method, is a function that does some statistical operation, in this case minimum, across the dimensions that we include in as its argument. In this case, we included latitude and longitude, and whatever is left remains on the output. If we didn't stick any argument in there, it would just minimize over everything and we get a single value out. And so, barring all the issues I had, I thought we maybe would have some time to explore, but just looking at where we're at, not sure we have much time for that, so I just encourage you outside of this session in particular, is that there are a lot of other calculations and things that you can look into when you're trying to explore a multidimensional data set. So I'd really encourage you to explore the MetPy docs. If you wanted to, you can dot and shift tab through and explore interactively in your Jupyter lab what these sort of methods could be. It might get overwhelming because there are a lot of them. And also, there are a lot of libraries that help support this. So I really encourage you to use this as a springboard into a lot of other exploration. And looking ahead, there are some of those later in this workshop. So stay tuned and keep an eye out for all kinds of interesting stuff in this broader ecosystem that's supported by the foundation of NetCDF and X-ray. So with that, I can pull up my sort of summary slide here. Let's see if we're going to cooperate. It's not cooperating. Great, there we go, it's back. Sorry about all the little issues along the way, but that's basically what we have for multidimensional exploratory analysis and some sort of questions for pondering or thinking if you want to take away. Otherwise, I can take any particular questions now. So thank you.
Thanks, Jon. We've got time for a couple questions, so Any questions online? We'll maybe pause for a minute, allow people to type if they have questions. I know as people were exploring different data sets, they were running into issues because, of course, names of dimensions or names of variables changed, the times changed slightly. I think it really goes to demonstrate, as I was working through the different data set, how important it is for all these exploratory data analysis pieces to then see, like, oh, yes, that's what this name is. Oh, this dimension name changed. And this is the challenge of our work, I think, and our grim data that present challenges for us. But we're good.
So you mentioned that for the X-array that many of the graphs you could make aren't publication ready. Is it because it's harder to control the formatting and specifics like you can with Matplotlib?
You can control them, but it's usually a matter of how you think about and structure a figure. Is that usually when you're trying to tell a story deliberately for a publication, you have a particular, here's the layout I want, here's where I want to go in this particular spot. And so it's more of a sort of philosophical choice that it's usually better to deliberately structure your figure with something designed for plotting rather than back out something that makes default assumptions for quick previews and try to adapt that into what you want. It's sort of, I'm taking a storytelling metaphor. It's like, do you plan out your story, your character arcs, what you want to happen, or do you hear some anecdotes and then try to, after the fact, explain, like, okay, this person said this, that means this happened. It's sort of a philosophical approach. You can usually do both with both approaches. It's just, where is your intention and where do you invest your effort at what time? At least that's how I'd look at it.
Okay, thank you.
Yeah, so I know like a lot of so far has been focused on like some of the different static plots and stuff for exploratory analysis. Do you have any recommendations for people? Because like you were showing, like when you're doing the initial, you do the point and click and stuff like that, and really dig into some of the different variables. Do you have any recommendations for people who want like more interactive plots and stuff like that with X-ray or any sort of toolkits to make it easier to interact instead of just the regular static plots?
Yeah, absolutely. So, and that's another thing, is one of many examples of tools that integrate with the X-ray ecosystem. I particularly recommend HVplot or HoloViews, or GeoViews specifically if you're working with geospatial data. Is that sort of the go-to open source in this ecosystem that allows you to have click and drag sliders and other things like that. There are certainly other tools in the ecosystem, but those are the sorts of things I'd really recommend talking to folks who have done this before, looking up and Googling examples and going to other documentation. There is by far nowhere near enough space in 30 minutes to explore all of those to any reasonable quality, unfortunately.
Could you repeat like some of the examples of the last example that you had mentioned?
Yeah, I think the easiest thing to look up is HoloViews. Yeah.
It's in the.
Did you just put it there? Yay, HVplot. Thank you. Oh, and PyVista and Plotly. Thank you. Thank you for everybody in chat. Yay! It's a collaborative effort. Collaborative success this time.
All right, let's thank Jon one more time.